We briefly mentioned before that the way we find the best line, the best fit into the dataset, is by minimizing the uh, total error associated with the model. And this principle is called the least squares principle. And it is what just it says. The principle says in order to find the best model, you have to find the line that minimizes those squared errors. Ideally, we want to minimize the size of all of the residuals. And if residuals is zero, we have a perfect line, which is uh, you don't see those type of situations in practice. So you cannot get it zero, but again, you try to minimize it to make it as small as possible. And the principle says that you choose the coefficient beta 0 and beta 1, so you basically choose your line so that the total sum of squared residuals is minimized. And it doesn't really matter whether you minimize the total sum of residuals, so average of the residuals, the result will be the same. All right. And it happens to be the case that for the simple linear model, for the when you just have y equal beta 0 plus beta 1x, the values of beta 0 and beta 1 that satisfy this least squares principle can be analytically calculated. And beta 0 is just the difference between average value of y minus beta 1 times x bar, and beta 1 is just correlation between x and y times the standard deviation in y and standard deviation in x. So actually, let's look at this principle and let's apply it to the Saratoga housing data set. Let's go back to R. So we're going to apply those formulas here. So let's calculate standard. So S of x is just standard deviation of the x, which is in our case is the living area. Okay. And standard deviation of y is the standard deviation of the price. So price was the okay. And then we have to calculate y bar and yx. Y bar is just the mean across all the values of x. So y bar is the mean across all values of x. So how's all the values of y, and x bar is the average across all the values of x, which is our living area. Okay, and now we can calculate beta 1. Beta 1 is equal, no, we also have the correlation between x and y is just the core function will do that for us. So correlation between the price and living area. So correlation between x and y. Now we're ready to calculate our beta 1. So that's our correlation between x and y times standard deviation in y divided by standard deviation in x. So let's calculate. Let's look at the value of beta 1, 0.11. So it's exactly the same value as the function ln found for us. And then beta 0 is y bar minus beta 1 times x bar. Okay, so let's look at the value of beta 0. We should see 13.43, so that's exactly the value that you remember that. Let's compare it with the values that the ln function found for us. So it's exactly the same values we see here. So it's one of the reasons we look at the squared errors and not the absolute. So you can ask, okay, so instead of maybe least squares principle is that you minimize So you take the sum across uh, residuals yi minus yi hat, and then you square them, and then you minimize the sum across all data points. So let me go back to the slide so you can see the formula. So that's the least squares principle. Now you can ask, okay, so we take the squares so we can avoid the cancellation of negatives and positives, but maybe instead of taking these squares, we can minimize the absolute value, yi minus yi I from 1 to n. So instead of taking squares, we can minimize absolute values of the residuals, and we also avoid the cancellation of negatives and positives in this way. However, we don't have a convenient solution. So this problem is hard to solve. And this problem is easy to solve. It's just mathematical properties of squares. Squares behave much nicer. It's a smoother function compared to the absolute values. And in the case when we only have one predictor, actually we can analytically calculate beta 0 and beta 1 that comes out of the least squares principle, which is not the case for this absolute value approach. So if you use absolute value, you won't be able to do something like that. And let's look at a few things. So one observation here is that the coefficient beta 1 is just proportional to the correlation, which makes sense. So the stronger the correlation, the higher the coefficient beta 1 is supposed to see. If there's no correlation between x and y, they are uncorrelated, then beta 1 will be 0, meaning that if x changes, we don't expect any change in y, or we cannot predict any change in y from the linear model. And another thing that comes out of from this model is that x bar and y bar are, so this point is on the line. Okay, if you plug in here x bar and y bar, you will actually see that so if you plug in x bar and y bar to this equation, so y bar equal beta 0 plus beta 1 x bar, you'll see that this relationship is satisfied. So you can do a little bit of math here, and you will see that it is indeed the case. So x bar and y bar is on the line. All right, and yeah, so those observations about those relationships, and another observation here is that so we can rewrite. So you remember beta 1 was the correlation between x and y times the ratio of standard deviations in y and x. If we write down explicitly what it is, you actually can simplify this expression, and what you get is you get covariance between x and y on the top, and variance of x is on the bottom. So it's the same relationship, just rewritten in a slightly modified way. Okay, so the estimate for the beta 1 coefficient is just the correlation R times the scaling factor, and scaling factor happens to be this ratio of standard deviations in y and x, and also it basically ensures that we have proper units, because you remember correlation is dimensionless, right? And standard deviations are measured. Standard deviations of y measured in the units of y, standard deviation of x measured in units of x. So beta 1 will be measured in units of y divided by the units of x. So units of beta 1 are the units of y divided by the units of x. All right, and one more concept here is imagine a situation when you take a data set. Let's say we take the Saratoga housing data set, and we feed a linear model to this data set. And then let's say we collect another data set next year from the same geographical area, from the Saratoga County, and we feed another model, we feed another line. Do you think this line will be the same or different? And since the data sets are slightly different, right, they were collected for different periods of time, And for different houses also, you should expect that those lines will be slightly different. So essentially what you have here, you have some sampling error associated with beta 1. If you go from one data set to another data set, your beta 1 will change. The line that fits into this cloud of the points will slightly change. And what you see here, I did this very simple experiment. So I took the Saratoga data set, and then I took subsample of the data set. So I basically selected a few rows, and I fitted value of beta 1 using only a few of those rows. And I did it many times. So each of those green lines is the linear model fitted to the subset of the data set. And you see, depending on which subset I take, my line will have slightly different slope. So essentially the slope is subject to the sampling error. Okay, so the beta 1 itself estimate of beta 1. An estimate is just the value that comes from the linear model estimation process, from the least square principle. The estimate of beta 1 is subject to sampling error. Okay. Now, we have a quantity which is subject to the sampling error, meaning that this quantity itself is random. So beta 1 is random. There is some uncertainty. There is uncertainty associated with beta 1. So when we get some value of beta 1 that comes out of the estimation procedure, we're not really certain whether that's the true beta 1, or if we take another data set, will we have the same beta 1 or will not. So that's a question. And it happens that beta 1 follows normal distribution. You remember when we talked about estimating uncertainty about the average estimated from the data set. So we have this convenient property. It's actually also the instance of central limit theorem, which says that the beta 1 itself will follow normal distribution. And we're going to center this normal distribution at the beta 1 hat. And the beta 1 hat is what is called an estimated value of the slope from given data. Okay. So again, if you take different subsets of the same data set, you will have slightly different beta 1 hats. Okay. But let's say you're given a data set, you estimate your beta 1, and then you say the true value of the beta is actually going to be normally distributed, and this normal distribution is going to be centered at this beta 1 hat value. And the standard deviation, or the variance S squared B, can actually analytically calculate, and this is the formula how you can calculate the variance for this normal distribution. So we have this very nice property of beta 1. We actually say, yes, we admit the fact it's uncertain, but the nice thing about this is that we actually can quantify this uncertainty, and we can precisely describe that it follows normal distribution, and we can have a very good guess about what the mean of the standard normal distribution will be, and what the standard deviation of this normal distribution is going to be. Okay, and and you can see what comes into this equation. There are three factors: the sample size n, which appears here on the bottom, meaning that if n goes higher, the standard deviation, or the variance associated with estimate of beta, the variance of beta 1 will go down, which makes sense. The more data we observe, the more confident we will be about the value of beta 1 that we estimate from this data set. Another value that comes here is the error variance. So that basically tells us how far values of the y are from the fitted line. And if this value s squared goes up, our variance for the beta 1 also will go up. Okay, and again, it's intuitively it's clear. If you have values of y that are far away from the line, then we should be very suspicious about the slope, and we say, okay, the variance of the slope is actually goes higher as the deviations of the y from the line goes higher. And another value is here the variance of x. So the variance of x, if it goes up, the variance of beta 1 goes down. Now, why is that? And the reason that we have this property is that the variance of x tells us how many different values of x we actually observed in the data set. And a good data set, a representative data set, will have different values of x. And you don't only have values of x that are centered around the average value of x, but you also have a lot of the values that are on the left tail and on the right tail of the distribution of this x. Essentially, it gives us a good representation about the population. So if you only observe houses that are around 300,000, then you will have a small variance in the values of x. And essentially, the model that you build will not be a high quality model if you try to predict, for example, for a house that potentially can be valued 500,000, because you only observed very specific types of the houses. So basically, variance of x tells you how many different types of the houses you observed in the data set, and you want this data set to be as diverse as possible. And the variance of x measures exactly that. All right, and then let's go back to the prediction interval. So we talked about the prediction interval for the yf, or y hat is the same thing here. So yf is the same as y hat. It's just prediction that comes out of the model. And so let's say we predict the new value of y for some specific value f x of f. And the prediction interval associated with this value of yf is given by this formula. And again, we can dissect it. There are several factors here. It's the same factors actually here. S squared, which is just the variance of the y's, how far they are from the line. If y's are far away from the line, then prediction interval is wider. So if this one is higher, then the prediction interval is wider. Okay, and then as n goes up, so the more samples we have, then prediction interval is narrower. So, and then we also have this how far this value of x of f from the average value of x. So if x of f is far, or so if the value is large, meaning that the x of f that we're trying to predict is far away from the average of x, then the prediction interval is wide. Okay? And again, so we basically say you're trying to predict for some value of x which is far away from the average value of x, then we should be uncertain about this type of prediction. And you also see this value s squared of x, so the variance in the values of x that we have in the data set. So if this goes up, the prediction interval becomes more and more narrow, meaning that the more diverse data set you have, the more confident you should be about the prediction generated by the model. So that's the intuition behind this equation. All right, so let's talk about the prediction error. A large predictive error basically means that we have high uncertainty, and it comes out from these factors: large S, large deviations of values of y from the line; small n, not enough data set; small s of x, not enough spread in the covariance, not enough diversity in the incoming data set; and large difference between x of f and x bar, which means we're trying to predict an extreme, and linear model should be very you should be very suspicious about those cases when you try to predict the extremes. Um, as a practical matter, the low value of s are more important for prediction than high r squared values. And let us talk quickly about r squared values.